So I'll begin with some exercise related to the things we have studied last week. This is an additional exercise related to lecture 2. Lecture 2 was about the differentiation and the integration of vector function. What is vector functions? We have studied vector functions like r of t, which is x of t, y of t, z of t. So x and y and z, all of them depend on the parameter t, or f of t, any notations, f of t, g of t, h of t, whatever notation you like, or you are given. The question says, if r of t, the magnitude of the vector, r is constant. So whatever t is, the distance from the origin is the same. All like this. This is a point moving such that at every time it has the same magnitude, has the same distance from the origin. The question asks you to prove, the question asks you to prove that at all times, r of t, the position vector, and the derivative vector, the velocity vector, the tangent vector, they are orthogonal. R and r prime are orthogonal. What orthogonal is? Orthogonal means that these two vectors have 90-degree angle in between, or pi over 2 in radians. How to prove this? How to prove that two vectors are orthogonal or perpendicular? In other words, this means their dot product is 0. Two vectors are orthogonal if and only if their dot product is 0. Dot product means to multiply the first by the first, the second by the second, the third by the third, and to add all of these together. Okay? Okay, we know that the magnitude of the vector r, ABC, r is given by ABC. Its magnitude is written this way or this way. This is the magnitude of the vector. The length of the vector is given by the Pythagoras formula, a square plus b square plus c square under the square root, the radical. So it's a square. The square of the magnitude is the same thing without the radical sign. But notice that r dot itself means ABC dot ABC again. How to do this dot product? Multiply the first to get a square plus the second plus the third to get c square. This is the quantity r dot r. So this is the same as this. So we have magnitude r square is the same as r dot r. So this is the beginning of the solution. This remark is the beginning of the solution. The beginning of solution here. So we are given that magnitude of r is constant. This means the square of the magnitude is constant as well. If you are worried about this prime to make ambiguity with the derivative, we can say is a new constant k. K, a new constant as well. So c square is a new constant. So now differentiate. Yes, write r dot r instead of magnitude r square and differentiate. What is the rule of differentiation? You know the rule of differentiation, f multiplied by g. Here is f vector dot v g vector. You get f dot g prime plus f prime dot g. This is the form of the product rule in case of vector functions. This is the rule of product rule of differentiation, you know, before from secondary school as well. But here in vectors, it looks like this. The first vector function dot the derivative of the second plus the derivative of the second dot the first. But notice that they are the same. These are the same because dot product a dot b is the same as b dot a. So it's commutative. So we get what? 2 times r dot r dr by dt. This means twice the quantity is 0. Therefore, this quantity is 0. This quantity is 0. What this quantity is? Vector a dot vector b equals 0. Therefore, if and only if a perpendicular to b. This is the required, the end of the proof. So it needs some ideas from before. If these formulas are clear to you, it will be very easy. If they're not clear to you, please write them, write these formulas, make revision of vectors, attend the revision. The revision will be made about these vectors stuff and geometry to be familiar with this stuff in our course. That's it. This proves that the vector R with the vector R prime or dr by dt are orthogonal or perpendicular or have 90-degree angle in between, with which way you like it. Any question about this? Do you hear me?
Yes.
Any problem about this?
No.
Okay. So let's go to the new lesson, which is lecture 3 about arc length of a vector and curvature. I have a clear one for you. This just prepared the main ideas and I'll solve with you the problems and study the concepts. So lecture 3 again about the arc length of a vector. We have a vector here, say vector gamma, which is in 2D xy or 3D xyz. So S here is given by y as a function of x, and x varies from A to B. What was the length of the curve from A to B? Anyone can remind us with this formula? Okay, if y is differentiable function, then that means we can find f prime along this interval. So we integrate from x equals a up to x equals b, this complicated form. 1 plus, it's not that complicated, it's very similar to the magnitude of the vector, Pythagoras theorem, and this stuff. F prime of x all square. The derivative of 1 plus f prime x all square, integrate all of this but with respect to x. From where this formula come, I will give you a proof in 3D, in the general situation. We have another form of this formula. If we are given the parametric form of the curve, I mean, if x depends on t, y depends on t, means R, like the way we write here in this course, f of t, g of t, no z. We are in 2D here in this part of this page, or x of t, y of t. And t varies from A to B. The same situation, but very symmetric formula. It's nicer formula than the one before, the one above. It's f prime of t, derivative of f square plus derivative of g square. It's a bit symmetric, so it's easier. The square root with respect to t. So differentiate x, differentiate y, square them, add, take the square root, integrate. We have many integrations to do in this lecture and the lecture to come. So why is this? Why is this? We will have a proof today for this formula. But we will do it in using vectors and using 3D, using the general situation. Same way in 3D, assume that a curve is given by the vector function r of t, which is x of t, y of t, z of t, or this way, f, g, h, and so on. So what we'll have here, this is the curve, this is the origin, this is the position vector at time t, This is the position vector after a little change of time t. This is the position vector at time plus delta t. So this vector will be delta r. So its magnitude is, and this is the arc length required to be calculated, ds, delta s or ds. Delta s is very similar or very near to delta r, but delta r, magnitude of delta r. If we divide this curve into infinitesimal parts, they will be the same when n tends to infinity. When we divide into n parts, when we divide this curve into n parts and n is very large, delta r and delta s will be the same. So we get this situation. S is integral of ds. As you know from integration, the integration is a summation of many things divided infinitesimally to very tiny things summed together. So this is from t equals a into t equals b ds by dt times dt. And this is absolute value of dr by dt. Because ds is very near to dr when we divide the curve infinitesimally from t equals a up to b. What is dr by dt? Magnitude of this vector. So this is the r vector function given. How to find the magnitude of its derivative for r prime of t? Like this is easier, from t equals a up to b. How to write this magnitude? This magnitude is written as f prime of t square plus y prime because this is the derivative. So you differentiate r of t to get f dash t, g dash t, h dash t, and so on. The g prime of t square plus h prime of t square. Or write it the other way. I will put it another way. This is from a equals up to b, from t equals a up to b. Or using this notation, x dot square plus y, get rid of these brackets and write this, x dot square plus y dot square plus z dot square, all of this under the radical dt. This is the proof. This as well works for the case of 2-dimension. The same situation, but we proved it generally here in 3D using vector functions. Any question? So we have new variable today for curves. We have t before. T was the time. S is the arc length. T capital was tangent vector, unit tangent vector, and so on. This is what we have studied. Any question? So how to find the arc length of a curve in 3D or 2D given functions? We differentiate and apply this formula. This is a very important formula. Look at here, S depends on T. So we can change, remark, S can be changed with T to give a new parameterization. Like this one in this example. So let's have some example. Any question before going into the example? Okay. So let's solve this example. You are given a helix, vertical helix. This is, as you see, a cosine t and a sine t. This is a circle, but we are not in 2D. So we have to look at Z. Z is not fixed, so we are not in a plane. It's not a circle. This circle is moving up in the Z direction. So what we have here, this is X, Y, and Z. When T is 0, A cosine 0 is A, so it begins here. A, 0, 0, and goes like this, 0, A, 0, and so on. It goes to try to complete the circle, but it goes up in the Z direction, in this direction. Why in this direction? Because at the beginning, at T equals 0, we were here. We were at this point, and go in this direction. This is all if A is positive. This is the direction of motion. And so on. This is the way, this is the sort of sketch we are asked to do. Now we need to find the arc length of this curve in some interval from the, T equals 0 up to T equals pi. Here T equals pi over 2. When we get cosine 0 and sine 1. Now let's find, this is R, A cosine T. Let's find the derivative. Why is the derivative? Because the formula is modulus R prime dt. That's it. A sine T, C T. So what is R prime? Differentiate d by dt of both sides to get derivative of cosine is sine, negative sine, of course. This derivative of sine is cosine. Derivative of CT is C. What is the magnitude of R prime? Magnitude. This is the magnitude. We revised this many times. How to find the magnitude of a vector? This is the square root of x dot square plus y dot square plus z dot square. This is negative A sine T plus A cosine T plus T square. And be careful, this is, you can always simplify. So many of the times you can simplify and get nice results. Don't carry it with you all the steps. What we have here is square common factor. Notice that this negative sign will be positive after squaring. So we get A square sine square plus A square cosine square. So we get sine square T plus cosine square T, which is 1. This is 1 plus T square. So the result is A square plus T square. Result of what? The magnitude. Now apply the formula for arc length. What is that? This is the formula, or this is the formula, the one you like. They are the same anyway. This is easier. So apply the arc length formula. What is that? S equals, you need to find the length from 0 to 2 pi. Okay, this is the length from 0 to 2 pi. This is the magnitude of R prime dt. We prepared this and we need to integrate. Notice that many integrations you need to do in this course. So put the formulas of integration before you and use them step by step to be familiar with them all the time. This is a constant. This is a constant, so it goes outside the, can be taken outside the integral and integrate dt from 0 to 2 pi. Integrate 1 dt is t. So we get what? A square plus t square. This is the result of the integral t from 0 to 2 pi. Then substitute from the upper bound to get 2 pi, subtract the lower bound to get 0. This is the result. It is square root of a square plus c square two pi. Better to write it 2 pi a square plus c square. And notice that this is the hypotenuse of a triangle whose legs are 2 pi a and 2 pi c. By Pythagoras, we get this hypotenuse here. 2 pi by Pythagoras here. This is the answer. This is the length of this helix from the time t equals 0 till the time t equals 2 pi. We were asked last time to draw r prime at some point. This can be asked again as well. So it is the same given curve, and you will be asked to find many parameters around it. Its position vector, its tangent vector capital T, its arc length, its a curvature, which to come in this lecture. The second part is, number 2, is how to represent R as a function of arc length S. So R of S. Yeah, he asks you to change, to transform R of T as a function of T, find it as a function of S. How to do that? We use the same arc length formula, but without this bound 2 pi. We put any general bound capital T or little t. This is easy. Second part. Second, to change R of T into R of S. Do you hear me? Is there any problem?
No, doctor, we can hear.
Okay. To change R of T into R of S, we do the same. Use arc length formula as above, but with not up to 2t, 2 pi, but to t. Formula from 0 to t. S equals integral from 0 to t instead of 2 pi. Of what? R prime dot R prime, no square here. This is a square root. R prime dot dt. So what we get the same answer before, but we stop here. We change this into t, we change this into t, we change this into t, and so on. So we get what at the end? Anyone to help? Square root of a square plus c square, integral of what? 1 dt from 0 to t, which is square root of a square plus c square times t from 0 to t. This means square root of a square plus c square times t. So this is depends on this t this way. So how to get rid of t and put s, divide by this square root. So t equals s over square root of a square plus c square. This is the required transformation. Why we do this? Because he asks me to change from a function of t into a function of s. He asks me to find the parameterization instead of the time, but the parameterization in terms of the arc length s. So at the end, we move every t and put instead of it the value s over the square root of a square plus c square. So we write it again from the beginning, r equals a cosine, a sine, and ct. So let's do that. A cosine t, a sine t, ct. Change every t here into its value with respect to s in terms of s. So it is a cosine, this value s over the root, a sine, s over this root, This parameterization is called the canonical parameterization of the curve because it depends on an important property of the curve, which is its length. T is S, so it's CS over the square root of A square C plus C square. This is the end of the solution. Any question? Is it clear, شباب?
Yes, doctor.
Okay. So 2 questions here are possible for the arc length. First one, to give you some interval and ask you to find the arc length of the curve in this interval. And the second question is to represent R as a function of arc length S instead of T. Second part of the lecture is about the second concept. Again, I'll show you the title to be aware of what's going on. Lecture 3 about space curves, vector functions representing a curve in space. We find what? We find the arc length S and the curvature kappa. This K is called kappa. It is the K in Greek. It is written some way curved in curved manner. Okay. So what is kappa? What is kappa is a measure for the curvature of the curve. What is the curvature of the curve? For example, if we have a straight line, if you have a straight line L, so you have no curvature. If you are moving or driving along a straight line, you feel no curvature at all, no curving. But some other curves are gentle curves. Gentle curves means the change is slow with respect to S. So every S units you move on the curve, there is some rate of change of the curve, which is measured by the rate of change of T with respect to S. So this is dt, rate of change of the tangent vector representing the curve, divided by S. S is the arc length we are studying, but we take the absolute value or the magnitude of this computation because K is a scalar quantity, not a vector quantity. So, but T is a vector, so we take the magnitude after the derivation. Scalar quantity. Measuring the curvature. How curvy is the curve? Curvature of the curve. But if we have not gentle curve changing slowly, we have sharp curve in which we have S here. If we move S, space, S. So look at T here, changes what? Changes rapidly, changes. The same amount of distance moved here, but very big difference in the change of T happening in this curve to the right. So this is curve 1, gentle curve, T changes slowly. Here curve 2, what happens? Sharp curve, T changes slowly, T changes rapidly, sorry. So kappa 2 is dt of this curve by ds, dt in curve 2 is less than that. This is bigger curvature. So you feel when you drive along sharp curve, you feel it's a bit difficult, very difficult to move, very difficult to drive, very dangerous to drive along. So some calculations and measures should be made before doing the curvature of the curves. So how to do this mathematically speaking? Mathematically, this is the definition. This is Formula 1. Not Formula 1, the race, but Formula 1 of calculating the curvature of the curve. Why is this Formula 1? Because look here, up there, when we need to calculate the curvature, we need to use this formula, depending on S, to find from R, it's R prime. R prime is the tangent vector divided by its magnitude to get its unit tangent vector capital T, then differentiate with respect to the arc length S. But this is a bit difficult, a bit tedious calculation. So we are looking for other formulas from this definition. So we have many formulas to go. I'll show all of them first and then choose the best of them to use in our examples. The second formula for calculating the curvature of a curve is not to use S. But S, this was of great benefit to understand what's going on. What's going on with respect to S when we move. When we move S units along the curve, how that curve changed, this was the definition of the curvature, dt by ds, rate of change of the unit vector t with respect to arc length S. Now we need to differentiate with respect to t, the little t, which is the time. This is easier in calculus because we are usually given r as a function of t. So what to do? What to do? Use the chain rule of differentiation. Chain rule of differentiation says dt by dt is dt by ds times ds by dt. What is going on? This is the chain rule of differentiation. ds down, ds up. The same thing in the left. What is going on here? dt by ds. When we take its magnitude, we get the curvature. So isolated or solve for dt by ds to calculate kappa from it. Then we have t prime divided by ds dt. From the right, this is t prime divided by the magnitude of r prime, because we know before delta s is delta r. So when they are infinitesimal, ds is tr. So ds by dt is dr by dt. dr by dt is the tangent vector r prime. This is the formula. This is the formula I mean. dt by ds, to take the magnitude of the left-hand side, then we take the magnitude of the right-hand side. Therefore, kappa equals the curvature equals this. This is formula 2. What is there? There is, we have the r, given r, we find r prime, we find t prime, yes. From r prime, we find t, then we find t prime. So we will make derivatives twice, and then divide by the magnitude of the first derivative. This is not bad, but still to go, we have something better and easier than that. So it's still a bit lengthy calculation to go, which is, I'll put it in a square, this one. This is the third formula for kappa. Kappa given by the magnitude of the cross product A cross B, vector A cross vector B, cross Cartesian product vector B, which is given by, as you know before, I, J, K, vector, unit vectors. Here, components of A, component of A, third component of A, components of B, second, third, and then computed to get new vector. What is the new vector? You know before we have, if we have A in this way, B in this way, you go A cross B is a vector perpendicular to both of them, making angle, right angle with A, right angle with B. You know the right-hand rule? Right-hand rule in physics to determine the direction of A cross B. No problem, we don't need the right-hand rule or anything here. We need to know, to remind ourselves with the, how to compute this stuff. The proof of this formula, the third formula, is a bit lengthy. We are not given here. What it says, the important thing, what it says if you are given the vector function R of t, find its first derivative, find the first derivative of R, second derivative of R, then cross them using the vector product. Get the magnitude of this cross product vector. So one, find first derivative, second derivative, their cross product, the magnitude of this cross product. This is the first step. We find the numerator. Second, we find the magnitude of the first derivative. We already have the R prime. We get its magnitude. As usual, magnitude of a vector. Square root of the x square plus y square plus z square. Or a square plus b square plus c square, whatever notation you have. Then cube this and simplify each step. Divide the result you have here and here. This is a formula for calculating the curvature of a given vector. It is the easiest formula for a space curve. We have the last formula we have is, this is the third formula. The last formula we have, it's only applicable for 2D curve when y is a function of x, like this. When we have xy only, and we have a curve like y equals ln x, function of x, or y equals e to the x, or y equals x square, parabola, whatever plane curve we have, we can apply this formula. From where do you get this formula? It is easy exercise on the formulas before. But this is not applicable for a space curve because there is no vector here. It can be deduced from the vectors we have already. What it says the second derivative of the function divided by this compound, this quantity, to the power 3/2, 3 halves. 1 plus the first derivative square. I think we see this first derivative square, 1 plus first derivative square once before here. Yes, it is in the arc length formula from 2D. Yes, exactly. So the arc length and curvature are very related. Let's recap. What is, do you hear me first?
Yes, doctor.
Katrina? Are you with me?
أيوة دكتور.
You understand me? Okay. Any question?
No, thank you.
Okay, you need to collect all of these formulas in one page, put them before you and use them in exercises. And in the examples I give you and your worksheet for tonight will be easy, inshallah. It's a bit lengthy calculations, but easy. I'll solve with you examples in details.
دكتور سوري، انا دلوقتي مش عارفه الاقي الباوربوينتس القديمه اللي هي زي دول القديمه. انا كنت عشان كده عايزه اسال حضرتك.
PowerPoints of the, but it does not contain any solutions.
ايوه اللي هو like الاكزامبلز قصدي، اللي هو like يعني شايف ازاي حضرتك كل حصه بتفتح البتاعه دي وبتسولف معانا.
ايوه.
او do you upload it ولا لا؟
I didn't. The PowerPoint can be uploaded. I'll send you them, no problem.
Okay, thank you doctor.
You're welcome. Katrina is gone. Okay, so let's have some example. So let's go for calculating the curvature of a straight line, curvature of a helix, and what the time allows us to do. Are you with me, Muhammad?
Yes, doctor.
Okay, no one else? No problem, you're welcome. Okay, this is the example we have before. Given the vertical circular helix, vertical, because it's along Z, it is the same example we have before, given along the direction of Z. The circle in XY direction, and it moves up or down in the Z direction. Find the curvature. What is the best way to do here if you are given a curve?
I think the easiest way would be the R dash cross R double dash over R dash power 3, the
Yes,
one that we wrote.
This is what we will do. I'll divide it. Look, this is the formula, the easiest formula to use. But let's divide it into some parts. We need to compute R prime, R double prime, and cross them, divide. This is the first part. I'll divide it according to the grades we do for R prime cross R double prime. Then its magnitude. So we do this and then compute the magnitude. Third part is to compute the magnitude of R prime. We should have already the vector R prime. Find its magnitude and its magnitude cube. And then divide this by this to get K. Curvature is this by this. Again, I write it from my mind. R prime, in my memory, R prime cross R double prime divided by R prime magnitude cube. This is the formula. So this is the algorithm or the method to do, to apply this formula. So we are given R. Let's move this. Given R equals A cosine T, A sine T, CT. So take derivative.
تبقى negative A sin T و A cosine T.
We get R prime, negative A sine T, A cosine T, and C. The derivative of CT is C, only C. The second derivative again,
negative A
differentiate to get negative A cosine T, negative A sine T, and 0. Okay. This will be needed again. Let's name this equation 1 because we will need it when we divide by its magnitude cube. So keep it numbered to have reference for it. Yes, what's your question?
هو الماجنتيود بتاع الار داش هيبقى a squared plus c squared صح؟ عشان الساين سكوير ده تروح على
it will, but do it slowly, bit by bit, please. Okay, so let's find the cross product of two vectors, as I mentioned, ijk determinant, and then let's copy the components from the given one, from the ones we calculated. ijk. The components of R prime, negative A sine T, A cosine T, C. Components of R double prime, negative A cosine T, negative A sine T, and 0. How to compute this is a new vector. How to compute? Like this. In the direction of I, so cover I, row and column. Cover the row, the I and J, and the row and column containing the I. This will give you the I component, and expand this part you find. This 2 by 2 determinant.
So it will be 0 plus AC sin t.
Yes, exactly. When we
minus.
multiply this is plus, this is minus. Yes.
Then we'll have minus for the J components. It will be 0 minus.
Wait,
oh, no, 0
let's write the I component first.
Okay.
0 minus, so it will be plus AC sin t, comma, the J component. Let's copy this again, this determinant. I'll put it here in details to show you what to cover, what to remove.
وانا
Okay.
فاكرها، انا عارفها اللي هي اللي
Okay.
ازاي اعملها. قشطة، ممكن اعملها على طول.
So this is A cosine t, this is C, this is, yes. Now we cover the J. To find the J component, remove the J row and the J column. You get this 2 by 2 determinant, the green one. Multiply and cross multiply. This is positive, this is negative, and get the result. The result of the green determinant will be 0 minus again, which is A minus, so it's plus AC cosine t.
طب
Got
دكتور،
it?
عندي سؤال.
Yes?
هي مش المفروض هتبقى نيجاتيف برضه عشان هي عند الجي كومبوننت بتبقى نيجاتيف؟
Yes, right, you are. Great. This is negative, this is positive, this is positive again. Exactly. So we have negative sign here. Great. Again.
الكي كومبوننت بقى يبقى A squared
For the key component, let's what? Negative A sign, A cosine. So let's move this, remove this first. A cosine C, and here we have negative A cosine, negative A sine, and here 0. So again, we cover this row and this column containing K, and getting the value of the 2 by 2 determinant we still have. The 2, this is the 1. This is plus, and this is minus as well. So what we get?
A squared sin squared?
Yes, exactly. A squared sine square t. Then
Plus?
minus what? Minus, so it will be plus again, A square cosine square t.
Yes. Then we get the magnitude of.
Yeah, first of all, to simplify first. Before the magnitude, simplify.
ماشي، احنا لو خدنا ال A
We
common
have
factor.
here sine square plus cosine square, so we simplify first. Then what we have?
if we simplified يعني.
Yes, sine square plus cosine square is the usual simplification we have.
Okay, so if we took the A common factor, it will be 1. So A times 1.
So this is R prime cross R double prime. This is the cross product of the vector. So let's simplify A C sine t. Then what? Negative A C cosine t. Then what? A square times 1. This is A square times the usual one we have when we the identity sine square plus cosine square. This is No, we still to find its magnitude. Then the magnitude. So what again, recap. First part is
get the R dash and the R double dash. Then
first and second derivative found. Second, we find the cross product of the derivative and its magnitude. Done. Third, we find the magnitude of R prime. Sorry, not yet. Where is the magnitude? Yes, let's do the magnitude. Magnitude of R prime cross R double prime is square root of
A squared, C squared, we can take it as a common factor. So
yes,
we have
exactly. Yes, sine square t plus A square C square cosine square t. As you said, you can omit this step and do it directly. This is the case. Here, you can get, as you said, A square C square common factor. Here, the A square to be squared as well.
Yes.
So I like to make it step by step, not to forget any part, because this would be missed. So A square C square common factor, we get the one from the sine square plus cosine square. Here we get A4. Again, A square is common factor. We get A square, C square plus A square. Of course, it is commutative, but to show our work clearly, this is the A times the square root of A square plus C square. This is the magnitude we need to find. This is the numerator. This is the numerator of the formula of curvature. So we have, this is part I, this is double I, we need to find, we need to number it, double I. Third part is to find the magnitude of R prime at its cube. So what's R prime first of all? R prime is here.
So negative A cosine t, negative
Yes.
A sine t, and 0.
Wait a second. Okay. Let's have it here. Okay. This is R prime. So R prime, magnitude of R prime is?
It will be A squared plus C squared.
Yes. A square sine square t plus A square cosine square t plus C square. This can be simplified into A square plus C square. And hence, R prime cube, when you cube this, what you get? When you square it, you get rid of the square root.
Yes.
So you get this and multiply it once again by R prime. So we can write it this way. It's R prime magnitude squared times R prime magnitude of R prime. This will give you A square plus C square times the square root of A square plus C square. Exactly. This is 2 and this is 3. This is to be divided 2 by 3. 2 divided by 3 will give you kappa, which is, the formula is R prime cross R double prime. Their magnitude divided by the magnitude of R prime cube, which is from 2 to 3, 2 up to 3. So we have A square root A square plus C square divided by A square plus C square times the square root.
We can cancel the square root with each other?
Sure, because this is multiplication.
Yes.
If this is multiplication, yes, you can cancel. Otherwise, you cannot. So the result, the final result is A over A squared plus C squared. So we can have some special cases here. Look at this. Special cases. Look at the original given function, A cosine, A sine, and CT. Is it?
No.
Yes, it is. Yes, it is. It's a curvature. This is the helix. Helix. What helix? Circular helix, because this is A and this is A. It's not elliptical helix as the example we had last week. It is in the the z-axis is the axis of the helix because the movement is along the z-axis. In the xy direction, xy projection is a circle. So it's a circular vertical helix. What happens if C is 0? So it's a special case. Case 1, when C equals 0. What happens? This C equals 0, so it's not a helix at all. It is a what? C is 0, it's a circle. Circle in the XY plane. Center 0 and radius A, which is x squared plus y squared equals A squared. Yes. A cosine T squared plus A sine T squared is x squared plus y squared is A squared. Yes, يبقى السنتر 0 0 radius A. Got it?
Yes.
Okay, the curvature of the circle, therefore the curvature of the circle is K of circle equals K kappa at C equals 0. Which is, what happens when C equals 0? It's A over A squared plus 0 squared. So it's A over A squared means 1 over A. So notice that it is a reciprocal of reciprocal of what? The radius of circle.
So, doctor, so if the k is equal to 0, we use case 4?
K equals 0. Where is K equals 0?
Or z equals 0?
Yes, Z equals 0. Yes, you can. You can begin from the beginning and apply the formula 4, but still, the ones we have is easier. The one we have is easier anyway. We can do it as well. If you are given R equals A cosine T, A sine T 0, you can use vectors and apply the formula 3 we have. It's already easy for all cases. You even the y as a function of x for the case of the circle is not nice. You can apply, yes, I'll write it for you. You can apply, you can apply formula 4. Y function of x. Here for circle, in case of circle, what we have? x square plus y square equals a square gives you y equals what? To solve for y to get plus or minus root a square minus x square. So you have this circle.
Can you say?
So you have two functions here. The positive one is square minus x square. Here the semicircle up and the semicircle below, which is this negative square root of a square minus x square. So the easiest solution is the one we introduced using vectors. Any question? Notice that this k is independent of t. So the helix has this property. Notice here that curvature of circular helix is independent of t. No t in the, after all of these given t's, cosine, sines, and all of that, we get rid of them. They all gone. And this is the remark for the circle. The curvature of the circle is the reciprocal of its radius. This means when we have a bigger circle, here, remark again, kappa of the circle is 1 over a. So as a increases, a goes to infinity, kappa goes to 0. A goes to 0, kappa goes to infinity. So very tiny circles, very large k, very large curvature. Imagine that you are driving along a very tiny circle. This will be very difficult because of this huge curvature. If you are moving very large circle, this is large circle, large circle, large circle, like this one, like, so it tends to seem like a line, straight line. So you don't feel the curvature. Got it?
Yes.
Okay. So let's solve one easier example. This can, as you said, you can use formula 4 for this. You make a differential of this twice, but it gets complicated because of the square root and first derivative and second derivative and all of this. But when using cosine and sine, this parametric equation, this parametric form makes life easier. So let's have some other example. I'll bring it from the previous lecture. Okay. What we are going to do now, we calculate the curvature for a straight line. To be sure that algebra and this calculus stuff go with our intuition of curvature, what curvature is. Our remark agree with what we expect for this case of helix, which changed into a circle, and then this circle changed into a straight line, where when its radius is very big, when A is very large, its curvature is very small, as you see. So let's have this problem. Example. Find curvature of number 1, a straight line, that's it. B, a parabola, straight line in space, a parabola in 2D. Say in the form y equals x squared plus bx plus c. So number 1 is very easy. And comment on the cases of coefficients. Okay. Number 1, what is the equation of a given line? Where is the given vector function? We know that straight line, we revised it last time, R is given by, or x, y, and z. We said last time that if a line passes through the point or a point x1, y1, z1, and has a directional vector a, b, c, a vector along this line, then x equals x1 plus at, so it's x1 plus at, y equals y1 plus bt. You can separate them in 3 equations or write them in 1 vector equation. So vectors simplify our life, right? 3 equations at once in 1 line, z1 plus ct. This is the case. A, B, C is fixed vector, constant vector along the line. x1, y1, z1 is a fixed point on this line. This what makes a line a line. It passes through a point and fixes the direction and does not change the direction at all. At all times, we have the same direction. So now, the easiest solution is to use this formula 3. What is the derivative you have here, Muhammad?
Derivative would be 1.
A.
A.
Yes,
Oh,
derivative of t is 1, but we have a coefficient here. x1 gives 0, same as b, same
B
as
and
c. Then, second derivative?
Would be 0, 0, and 0.
0, yes, 0 vector. Yes, 0 vector. You can write it simply like this. We have the derivatives, we got the 0 vector, therefore, cross product is ABC cross 0, 0, 0. So we get 0. Or write it simply like this. Times 0 is 0. That's it. Which is 0, 0, 0. This is better.
طب عندي سؤال يا دكتور.
اتفضل.
ليه ما استخدمناش هنا اللي هي الماجنتيود تي داش على ماجنتيود الار داش اللي هي بتاعت
Yes, you can. Yes, you can. Any formula you can use. I show you this is the easiest. I'll go to which one?
اللي هي ماجنتيود التي داش على ماجنتيود الار داش اللي هي
You can. T is ABC. We can do it another way. Yes, we can do it another way.
هو
طيب.
الاثنين يمشوا بس تبقى انه اسهل تبقى ال
Third formula is the easiest. I'll show you, I try to show you use of 2 as well. Okay, this is therefore magnitude of R prime cross R double prime is
0
0 square plus 0 square plus 0 square gives you 0. And what? Magnitude of r prime is root a square plus b square plus c square. This is cube of this gives you a square plus b square plus c square times the square root. Divide this by this
0.
to get 0. Therefore, kappa of curvature K يساوي R prime cross R double prime divided by R prime magnitude cube, which is 0 over non-zero, which is 0, of course. What is non-zero is this quantity, a square plus b square plus c square power 3 over 2, which is 0, as expected. What is expected? What do you expect the curvature to be of a straight line to be?
0.
Of course, it is a 0. Yes. Another solution for this, as you trying to do.
التانية هتعقد شوية عشان هتبقى الار داش على ماجنتيود الار داش وبعد كده على ال
Another solution, let's find what? Another k equals, what is the second formula?
ماجنتيود التي داش اوفر ماجنتيود الار داش.
Yes, t dash of t over r dash of t. T dash of t over r dash of t. R dash of t. Magnitude. So what is r dash here? R is x1 plus at, y1 plus bt, z1 plus ct. What are these variables? These are the point x1, y1, z1, the vector a, b, c. This is the line. So what is r dash?
A, B, and T.
Computed before, it's ABC. It is the directional vector. So T is, what is T?
R dash over magnitude R dash.
Yes, R dash vector over its magnitude to be a unit vector. R dash over its magnitude. So T is ABC divided by square root of a square plus b square plus c square. So this is t. We need to find its derivative. T dash is, differentiate this with respect to t. There is no t there. It gives you 0 vector. It's a constant vector. If you like to write it 0, 0, 0, it's this vector.
طب دكتور قول لي حضرتك حطيت ماجنتيود عند الار داش فالتي ايكوال مش المفروض لا اللي فوقيها مش المفروض تبقى ار داش على طول يعني مش ماجنتيود
No, r dash is a vector. Kappa is a scalar quantity. Has to be a scalar quantity. Here.
يعني قصدي
There is a magnitude for the vector in the numerator and the one in the denominator.
قصدي في كيس 2 اللي احنا بنعملها اللي هي تمام فهمت قصدي حضرتك.
Okay.
تمام.
So again, K is the T prime is 0 vector over what R prime of T? R prime of T is magnitude is root a square plus b square plus c square, which is 0. There is a magnitude here. Again, 0. The last example of the parabola, you can use, this is easy to apply your formula for. Because y is a function of x, explicit function, b, y is ax squared plus bx plus c. This represents a parabola as usual like this. So this is let y equal fx. We call it fx to apply the formula we have. Formula 4. This is f prime. This is direct differentiation, then double prime, and so on. 2ax plus b. This is the first derivative. And then ta is the second derivative. Apply the formula. The fourth formula for 2D curve, which is the second derivative kappa equals second derivative over 1 plus the first derivative square, all to the power of this compound. Do you remember? To the power of what?
Power 3.
3 over 2. Over 2 is instead of the square root we have for the norm or the magnitude of the vector. Got it?
Yes.
The magnitude of the vector is a square root, means power of half. This is the power of half we have. We have it's the same formula. It is the same formula. So what we have here is f double prime is 2a over 1 plus 2ax plus b
Square.
whole power 2. All of this to the power 3 over 2. Let's check this formula. Be sure it's right, the right one. Yes, it is. Yes, exactly. So I leave the other cases for A, B, and this stuff. What happens if A equals 0, for example, and this stuff. I think we are out of time. We'll stop here.